Now, we know then that the sampling distribution for the mean is normally distributed, okay, if the conditions are appropriate. It's normally distributed with the mean equal to the mean of the population, and the standard deviation is equal to the standard deviation of the population divided by the square root of it. Okay. Your book talks about one element that is that we need to include when we are dealing with finite populations. Okay, and that finite population correction factor. Okay, you are going to include the finite population correction factor in the standard deviation of the sampling distribution, and that is equal to the square root of n minus n divided by n minus 1, where n, capital N, is the size of your population, and small n is the size of your sample. Okay, and now, when do you know if this is finite or is not finite a population? Okay, if you have a infinite population, like the production of all the light bulbs during the day, you can consider that as an infinite population. The other way that you can say that it's an infinite population is when your sample size is less or equal than 5% of the whole population. So, for example, if I have the total population N, capital N, equal to 500, and I get sample, small n, equal to 50, what is the percentage taken? I mean, the percentage is n divided by n, that's equal to 50, divided by 500, that this is 0.1, and this is 10%. 10% is higher than 5%. That is the limit to consider finite, non-finite population. So in this case, since 10% is higher than 5%, then we need to include the finite population correction factor over here. Okay? Now, let's say that I have the population size equal to 5,000 and my sample size is again 50. Right? So the ratio is going to be 50 divided by 5,000, and it's going to be 0.01. It's only 1%, and 1% is less or equal than 5%. So we are going to assume that in this case we have an infinite population. So that is how we consider either include the finite population correction factor in the case that we have a finite population where the sample size is greater than 5%, or do not include it. This and this is the finite population correction factor. Okay. Now, what is the relationship between the sample size and the distribution? Okay. Let's say that I have my sampling distribution, and we know that the mean is equal to mu, and let's consider, let's say that this is an infinite population, and the sigma is equal to the standard deviation of the population divided by the square root of n. Now, what happened, let's say that this is n, for just an example, n equal to 30, and I have this one. What happened if I increase my sample size? If I increase my sample size, this number, the standard deviation, is going to be a smaller number. And the standard deviation tells you how spread the distribution is from the mean. So if I increase my sample size, I'm going to get something like this. A taller but thinner normal distribution that is also the mean is equal to mu, and the standard deviation is going to be sigma, but instead of a square root of 30, it's going to be of a square, let's say that n is equal to 100. Okay? So if I increase my sample size, I'm going to have a taller, thinner distribution. And if I increase my sample size, this is going to be smaller, and this, the standard deviation for the sampling distribution, is also called the standard error of the mean. Okay? The standard deviation for the sampling distribution is also called the standard error of the mean. And that's it. That's it. Let's do one problem. We have the point estimator that I'm not going to do that. So you do it, calculate the X bar, calculate S, and then from there you get the point estimators. Okay, let's do problem 19. Okay. Let's do problem 19. 19 on page 287 tells you a population has a mean of 200. A population has a mean of 200. So they are giving us the population mean, and that is mu, and is equal to 200. And the standard deviation equal to 50, standard deviation of the population. So sigma is equal to 50. Suppose that a random sample of size 100, so the sample size n is equal to 100, is selected, and X bar is used to estimate mu. Okay, what is the probability that the sample mean will be within plus minus 5 of the population mean? Okay, I have a normal distribution with the mean equal to the mean of the population, and that is mu, 200, and the standard deviation is equal to the standard deviation of the population divided by the square root of n, and that is equal to 50 divided by the square root of 100 equal to 5. So we have a normal distribution with mean equal to 200 and sigma equal to 5. And they are asking us what is the probability that the sample mean will be within plus minus 5 of the population mean. So they want to know what is this probability plus minus 5, so from 195 until 205. That's what the problem is asking us. How do you find this probability? The only way that you can find this probability is to transform this standard distribution, this normal distribution, into a standard normal distribution with mean equal to 0 and sigma equal to 1. Okay? And how do you do that? C is equal to x minus mu divided by sigma. And I want to know what is this C and what is this C, and this probability over here is exactly this probability over here. The only way to do that is trying to find out what is this Z that is this 195 in this distribution. So in order to do that, what is this 195 is C is equal to X, that is 185, minus mu, that is 200, divided by sigma, that is 5. And this is negative 1, so this is negative 1. Okay? And 205, what is 205? It's 205 minus 200 divided by 5, and this is positive 1, and this is positive 1. So if I found the probability between positive and negative 1, I'm going to find this probability that the value is between plus minus 5 of the population mean. So what I do is go to my table, find 1, positive 1, that is 0.8413, minus negative 1, that is 0.1587. If I do that, 0.84. That is equal to 0.6826. So, what the problem is asking me, what is the probability that it is between plus or minus 5 of the population mean is 0.6826, because this area over here, that is this area, plus or minus 1, is exactly this area over here, because we transformed this normal distribution into a standard normal distribution. And we get the probabilities from there. That's it. That's it.